Hello. So we have just seen how to evaluate the stability of a typical three-stage op-amp, and now we are going to explore one of the methods for frequency compensation so that we can make our system stable. And the method that we are going to see is sometimes termed Miller compensation, just because, as we will see, it makes use of the Miller effect. In essence, what we are going to do is shift the location of pole P1 to the left, because we have seen that basically our system was unstable because by the time we reach the 180 degrees phase shift, our gain is still greater than 1, greater than 0 dBs. However, if we shift the location of pole P1 to the left, in that direction, our gain will start rolling off sooner, and therefore by the time we reach the 180 degrees phase shift, hopefully our gain will be lower than 0 dBs. And that's how we will achieve stability. Now, a typical value of shifting is to achieve a phase margin of 45 degrees. That's not the only one. That's actually typically the minimum that we are going to go for. But typical values will be a phase margin of 45 degrees, 60 degrees, and 90 degrees. We're going to do our calculations and figure out what capacitor we need to introduce in our circuit, what's the value of the capacitor, in order to achieve a phase margin of 45 degrees. Now we can see by mere inspection that in this case, the dominant pole is pole number 1. And so that's the one we're going to be shifting. And so any capacitance that we introduce is going to be introduced at that location, at the location of node 1. So basically, we're going to introduce a capacitor effectively in parallel with CP1 to increase the equivalent capacitance at that node, thus shifting the pole P1 to the left to a lower frequency. To achieve a phase margin of 45 degrees, we will want that our 0 dB crossing point happens at exactly the location of P2. And the reason for that is we know at the location of P2, our phase shift is going to be 135 degrees, which is 45 degrees away from 180 degrees. And that will always be the case when we have a two-pole system like this one, where the two poles are sitting at different frequencies. So the frequency at which P2 is sitting is going to be the 135 degrees phase shift location. So just to write the question is, what value of capacitance will achieve phase margin equal to 45 degrees? And the answer is, to achieve a phase margin of 45 degrees, must shift the location of P1 so that the A equals 0 dB point occurs exactly at FP2. Okay, and that is since the phase shift associated with FP2 is exactly 135 degrees. Now I mentioned we're going to take advantage of the Miller effect. And the reason for that is if I just connect a capacitor like that in parallel from my node to ground, yes, I'm going to achieve the effect of shifting my pole P1, but I'm probably going to need to use a very large capacitor. Whereas if you remember, when we studied the Miller effect, we said that in essence, a capacitor connected in the feedback path of a gain amplifier was equivalent to connecting a capacitance at the input, which was equal to 1 minus the gain times the feedback capacitor, or approximately the gain the gain times the feedback capacitor. So a capacitor that is, in this case, 10 times larger can be seen at the input if I connect a capacitor in the feedback path. Therefore, I'm going to connect my capacitor in the following fashion as a feedback capacitor. And in essence, what I'm going to get is an equivalent capacitance at the input, which is going to be equal to CF approximately multiplied times 10, an equivalent capacitance at the output as well. I'm just going to care mostly about the capacitance at the input, because that's going to determine how much my P1 pole is shifting. But we'll talk about the effect of the output capacitance after our analysis. So basically, the first thing that we're going to do is determine the new location of dominant pole, and I'm going to refer to it as FP1 prime because it's the new location of P1. And so basically my FP1 prime is going to be equal to FP2 divided by the gain, or FP2 is 10 meg, or 10 to the 7, divided by the gain, which was 10 to the 4, or 10,000. And so that gives me 10 to the 3, or 1 kilohertz. And so let's take a look at graphically what will happen with the system if I were to move my pole P1 to location 1 kilohertz. And I'm going to do that over the same graph so that we can see it more clearly. So I've shifted my P1. Now I have P1 prime located here. P1 has disappeared. I mean, it's been shifted. And so my gain is going to be constant up until that point. Then it's going to start going down at a rate of 20 dBs per decade. So at 10K, it's going to be sitting at 60 dBs. At 100K, it's going to be sitting at 40 dBs. At 1 meg, it's going to be sitting at 20 dBs. And at 10 meg, it's going to be sitting at exactly 0 dBs. So until we reach that P2, this is going down at a rate of negative 20 dBs per decade. And then after P2, it starts going down at a rate of negative 40 dBs per decade. And with my phase, something similar happens. Up until 1/10 of the new location of P1, I'm going to have approximately 0 phase shift. And then at exactly the location of P1, I'm going to be sitting at minus 45 degrees. At 10 times that frequency, I'll be sitting at negative 90, where my phase is going to roll off at a rate of negative 45 degrees per decade. And then it's going to be approximately flat until I get to 1/10 of my location of P2, or 1 meg, after which point it's going to start going down at the rate of negative 45 degrees per decade, and then flatten out after 10 times the location of FP2. So this is also a rate of negative 45 degrees per decade. I can see now, just graphically, that my new phase margin is equal to 45 degrees, and that's by design. Essentially, the phase margin is going to be the difference in phase between the two key points. The point where my gain crosses the 0 dB point, which is this point, and the point where my phase shift reaches 180 degrees. So this is my new phase margin, which is by design 45 degrees. My new gain margin is going to be the difference in gain between those 2 points as well. And so it's going to be the difference in gain between the 0 dB crossing point and the point where I have reached negative 180 dB. Since my slope here is negative 40 dB per decade, and I'm reaching negative 180 one decade after 10 meg, then that means that my phase margin is now 40 dBs. So basically I'm at a minus 40 dB point by the time I reach the 180 degrees phase shift. Alright, so I have achieved stability for my sister. Now I need to figure out what's the value of capacitance that I need to connect in the feedback path in order to shift the pole by that amount, shift the pole to that frequency of 1 kilohertz. So I'm going to find value of capacitor to shift P1 to FP1 prime. And we have that FP1 prime is going to be equal to 1 over 2 pi R1 C1 prime. I'm going to refer to it as C1 prime because it is the new value of capacitance associated with node 1. That's going to be 1 over 2 pi. R1 is still the parallel combination of R out 1 and R in 2. And my new value of capacitance is going to be the sum of CP1 plus the Miller capacitance that I see at that node, C Miller 1. And so I want this frequency to sit at 1 kilohertz or 10 to the 3. And therefore I can solve for CP1 plus CM1. It's being equal to 1 over 2 pi. My R out 1 in parallel with R in 2, I'm going to approximate as 10K. And this will be 10 to the 3 or 1K. And so I get 50K divided by pi picofarads. For my C1 prime capacitance, my capacitance at the node number 1. Now, since CP1 is equal to 50 over pi, we can assume that CM1, my Miller capacitance at node 1, is much greater than CP1 because CP1 is 50 over pi and then CM1 plus CP1 is 50K over pi picofarads. Therefore, I'm going to approximate this as CP1 plus CM1 as being approximately equal to CM1. And so my C Miller capacitance at that point is going to be approximately equal to 50K divided by pi picofarads, which is due to the calculations, is around 16 nanofarads. So that's a large capacitor. Fortunately, we can take advantage of the Miller effect and the capacitance that we actually, or the capacitor that we actually need to connect in the feedback path in order to achieve the equivalent capacitance at the input node, at the node labeled 1, is going to be approximately that capacitance CM1 divided by the gain of the second stage. If you recall, Miller effect says that CM1 is equal to CF times 1 minus A2. Since A2 is negative 10, this will be CF times 11. To make calculations simple, I'm just going to approximate this as CF times 10 times the gain. And therefore, CF just needs to be equal to approximately CM1 divided by the gain, or 16 nanofarads divided by 10, which is 1.6 nanofarads. So that's great, that's a smaller capacitor. And it's going to give us the desired response. Now, I mentioned earlier that we have assumed that the location of P2 doesn't change by the introduction of this feedback capacitor, and that's technically not true. The location of the second pole will also change. And so, little note. we have assumed P2 or FP2 does not change with introduction of CF. In all reality, it changes, and it typically is going to be shifted to the right. So the frequency response at the output gets changed in a way that it is actually beneficial, because the location of P2 actually ends up shifting to a higher frequency, thus increasing our phase margin even further than the 45 that we had calculated. And so any electronics textbook will show you that the new location of FP2 prime, is going to be equal to 1 over 2 pi. I'm gonna times the following. Gm, obviously of the transistor in this gain stage, A2, times the feedback capacitance divided by Cp1 times Cp2 plus Cf, Cp1 plus Cp2. So that will be the new location for our FP2 frequency. Because FP2 ends up being shifted to a higher frequency, so FP2 gets shifted to a higher frequency. And because of that, this type of compensation is also referred to as pole splitting. Now, one thing that we haven't talked about much is about the amount of phase margin. Why is 45 degrees an interesting number? Well, for one thing, we have seen it's very easy to calculate, because then we need to make the 0 dB point as being located at exactly P2, or the frequency of P2. The reason why it is important, I'll put this as an additional design note. Importance of phase margin, PM. And the reason for that is the phase margin, it's also going to affect the time domain response of the circuit. And specifically, it's going to relate to the amount of ringing and overshoot that you will get in your step response. So PM phase margin determines amount of ringing and overshoot in your time domain response. So for example, I'm going to try to represent this graphically in a time domain plot. Let's imagine that this is V out in response to a step input. And I'm going to put it in different colors so that we can see the difference. So first I'm going to go ahead and put, for a small phase margin of, let's say, 30 degrees, I will get a lot of ringing and overshoot in my circuit, which is typically not a desirable effect. And depending on the application, you may be able to sustain more or less amount of overshoot. In the case of my 45 degrees phase margin, I'll still get some ringing and overshoot, but not quite as much as with a lower phase margin. So 45 degrees. With a 60 degree, which is another very common design target for the phase margin, I still technically get a little bit of overshoot, but not that much. So 60 degrees is a fairly good compromise. The amount of overshoot that I get is very small. It's about 1.3 times the final value. And in the case of, let's say, 90 degrees, which I can put with green, let's say, that would be a clearly overcompensated system. And so we can see the higher the phase margin, the less ringing and overshoot. The trade-off there is the speed of my system. Obviously, the smaller the phase margin, the faster my settling time is going to be. For the case of the 90 degrees phase margin, I'm going to have the slowest system, but slowest settling time, but I will get no overshoot. So perhaps make a little note there. There is a trade-off between ringing overshoot and speed. And this is something that we see clearly in the op-amps. Whenever we take a look at the schematic for an op-amp, we can see that in some cases, in most cases nowadays, we have a compensated, internally compensated op-amp. So if you look at the schematic, you will see a small capacitor placed between the output of the first stage, which is the input of the second stage, and the output of that second stage. So basically, across the feedback path of the second stage, there will be a compensating capacitor. For some op-amps, that compensating capacitor is not there. Those are referred to as uncompensated op-amps or sometimes decompensated op-amps. Now, when that is the case, the datasheet will typically specify the range of gains for which the op-amp will be stable, as well as they'll typically provide some external connections. So in case you wanted to increase the amount of compensation for your particular application, you will just have to connect your capacitor externally. But those will be basically faster op-amps. Why would you want a compensated op-amp instead of a decompensated one? Well, it's to guarantee the stability of your system. Why would you want a decompensated op-amp? And that's so that you can hopefully squeeze the last bit of performance out of your system, typically in terms of speed. You will note that the slew rates of internally compensated op-amps are going to be smaller typically than the slew rates of uncompensated op-amps. And the reason for that is the slew rate of an op-amp is directly related to that compensation capacitor. Specifically, perhaps the slew rate of an op-amp is related to compensation capacitor. Basically, that compensating capacitor, as you change your output voltage levels, has to charge and discharge. And there is some time associated with that charging and discharging of that capacitor. We know that the current through a capacitor is given by the equation IC equals C dV dt. And so the rate of change of voltage across a capacitor cannot be infinite unless you have infinite amount of current. Our supplies in our circuits typically cannot provide infinite amount of current. You're limited by the amount of current that your supply can provide, and therefore that limits your maximum rate of voltage change across that capacitor. It's going to be equal to IC divided by C. You can see that the larger the capacitance, the smaller the maximum rate of change of the voltage. And so the more compensated your circuit, the smaller the value of your slew rate. Okay. Higher the value of C, the smaller the slew rate of the op-amp. Notice also that this also explains that nonlinearity in the slew rate. In a linear system, we will expect that just like the charging and discharging of a capacitor. You expect to see a rounded response like this, just because the equivalent of a low-pass filter. However, when you're seeing the slew rate of an op-amp, what you see is a nonlinearity, let's say in response to a step response, until the op-amp is able to reach that final output voltage. And the reason for that is you can see also that dVdt, which is in essence, this is dVdt max, which is the slew rate of the op-amp. You can see that it is a constant quantity, IC divided by C, and so that gives us that constant slope. And so that's how the two are related. And I think that concludes our study of compensation.